Today we'll be doing the integral from 0 to 1 of the natural log of x plus 1 times the natural log of x divided by x dx. And to start off, we'll use the series representation of ln of x plus 1. So the natural log of x plus 1 is the sum from 1 to infinity, negative 1 to the k minus 1, x to the k over k. So is equal to the integral from 0 to 1 ln x over x, and the sum from 1 to infinity, negative 1 to the k minus 1, x to the k over k dx. And swapping the sum and integral, we have the sum from 1 to infinity, negative 1 to the k minus 1 over k, and the integral from 0 to 1 ln x over x times x to the k dx. This is equal to the sum from 1 to infinity, negative 1 to the k minus 1 over k, then the integral from 0 to 1 of x to the k minus 1 ln x dx. And we'll make a substitution. We'll let x equal e to the minus t, which means that dx equals negative e to the minus t dt, which also means that the natural log of x equals negative t, and that negative ln x equals t. So the bounds will be t sub 1 will be positive infinity, and t sub 2 will be 0. So this is equal to the sum from 1 to infinity, negative 1 to the k minus 1 over k, and the integral from infinity to 0 of x, but that's e to negative t to the k minus 1 power. Ln x will be times negative t, and dx is a negative e to negative t dt. And I'll use one of these negatives to flip the bounds of integration. So this is equal to the sum from 1 to infinity, negative 1 to the k minus 1 over k, and then the integral from 0 to infinity. So we have a e to the minus t, and we have a e to the negative t times k minus 1 times a negative t dt. And we can combine the exponents, so this is equal to the sum from 1 to infinity, negative 1 to the k minus 1 over k, and the integral from 0 to infinity of e to the negative t minus t times k minus 1 times negative t dt. And negative t minus t times k minus 1 is equal to negative t minus tk plus t, but that's equal to negative tk. So this is equal to the sum from 1 to infinity, negative 1 to the k minus 1 over k, and the integral from 0 to infinity, e to the negative tk times negative t dt. And from here we'll make another substitution. We'll let w equal tk, which means that dw equals k dt, and solving for dt, we have dt equals dw over k, and the bounds of integration will not change. So we're left with the sum from 1 to infinity, negative 1 to the k minus 1 over k, the integral from 0 to infinity of e to the minus w times negative t. If we solve for t, we have that w over k equals t. So minus w over k, and dt will be dw over k. So this is equal to, I'll factor out this negative. minus the sum from 1 to infinity, negative 1 to the k minus 1 over k, and then the integral from 0 to infinity of e to the minus w power w over k squared dw, and we could factor out the 1 over k squared. This is equal to negative the sum from 1 to infinity, negative 1 to the k minus 1 over k squared times k is k cubed, and the integral from 0 to infinity e to the minus w times w dw. But as you can notice that this integral is a gamma function evaluated at 2, but gamma 2 is 2 minus 1 factorial, which is 1 factorial, which is 1. So it's equal to negative the sum from 1 to infinity, negative 1 to the k minus 1 over k cubed, and this is negative the eta function evaluated at 3. But if we recall that the functional equation that eta s is 1 minus 2 to the 1 minus s power, and then zeta s. So we put a negative and put a 3. We have negative eta 3, negative 1 minus 2 raised to the 1 minus 3 power, and then we have a zeta 3. So negative eta 3 is equal to negative 1 minus 2 to the negative 2 power zeta 3, which is equal to negative 1 minus a fourth times zeta 3, which is negative 3/4 zeta 3. So you could say now that therefore the integral from 0 to 1 of the natural log of 1 plus x times the natural log of x over x dx is equal to negative 3/4 zeta 3. And this is the final result. Thank you very much for watching.